Doing all right. Doing okay. The audio was all right when I was chatting? Great. How we doing, folks? We all had fun doing some linear programming before spring break? Yes. Drawing lines. Cricket, you seem less excited about drawing lines. Fix that. Okay. All right. Just more sound effects. That's how. Now today we're going to talk a little bit about dynamics here. All right, just give people another minute. Glad to see all 50 of you here today. I'm rounding generously. All right, it's 9:30. It's perfect time. I hope. Well, first off, do people enjoy spring break? Good. Glad to hear it. Oh, it started recordings. Thank you very much, DJ. All right. Good to see you all. So, hope you enjoyed your spring break. We're going to drop our next homework assignment very soon on trajectory optimization, covering single shooting, multiple shooting, direct collocation. We're going to do a direct collocation example on Thursday. I really desperately wanted to get you an example last Thursday, but I had a catastrophic malfunction, as you saw, as my technical setup, so I apologize for that. But that's okay. I promise I'll get you guys a bonus lecture that's completely optional, just for fun, okay? You can watch. It's previously recorded, okay? So, but today, we're going to start pivoting from the control side back to the dynamics side a little bit. So let me just go here. Today, today's date, the 24th? No. 2026. 03. 24. So we have been doing a lot of control stuff. So if we look at what the course was covering, right? The course, we started off with doing some dynamical systems. Those are all our simulations, right? A lot of simulation in your first homework, right? Then we did a little bit of control, where we put a little controller on there, PD control on some of these systems. Then we started doing some optimization. Then we did some optimization of control. That specifically has been trajectory optimization and even a little MPC, which was a feedback controller, right? But for all of these topics here, I was giving you the physics of these systems, okay? In your first homework, I gave you the equations of motion for your pendulum on a cart, okay? I gave you the equations for how a tumor grows in a patient. I gave you those equations, right? And normally in a controls course, we assume that, someone gives us the equations, or we're able to derive the equations somehow. However, this is a mechanical engineering class, and a lot of our systems are mechanical systems. So given the fact that you all don't necessarily have a background in advanced dynamics, it's not required. You all take Dynamics 1, right? I love to give a little survival guide to advanced dynamics. That way you know how, also for your projects, okay? If you have anything that's pretty complicated, you have the tools you need to create your own simulations of multi-body dynamical systems, okay? What do I mean by multi-body, okay? But so I should have brought in a better example. We all know we have a single rigid body in our system, okay? Right? Like this. We could all derive the equations of motion. Crowd flies through the air. That's projectile motion, okay? Or if I put forces and torques on this one body, what all the accelerations are. I can use F equals ma, or torques are equal to I alpha. The sum of the torques are equal to I alpha in order to come up with the equations of motion for that system, okay? And you've done this many a time, Okay, we've done this many times in class for things like the pendulum, right? So we know we, to date, have been given system dynamics for us to control. Okay? And if we ever had to derive them, such as for the pendulum, so most examples where we derive dynamics have been using single rigid bodies. Okay? And if you take dynamics 1 in a dynamics class, that's often what you're dealing with. You're dealing with blocks that are sliding on different objects. There are springs attached to those blocks sometimes, okay? Springs, dampers, okay? And the way that you would typically get your equations of motion, you are using Newton's methods, Newtonian mechanics, where you have a free body diagram. You all know free body diagrams. You've done enough free body diagrams in your life, right? The idea is that you have some object, some potato. With that potato, got some center of mass. It's going to have some forces on it. Force 1, force 2, some forces up to force n. You got maybe some moments or torques on it. Torque 1, torque 2. And it's going to have some mass m and some inertia, rotational inertia I, right? Some mass and inertia. Okay? And so we all know, oh, how we get the equations of motion, the dynamics for this. Where we're going to sum all of our force vectors is going to be equal to mass times the acceleration vector. We know this. You're all very smart. The sum of all your torques, okay, it's going to be equal to I alpha, you know, if this is a planar body. Same thing applies for 3D dynamics, right? We're all just covering free body diagrams. Remember, free body diagrams. For those who are joining just now, free body diagrams, this is what they look like, right? Okay? And that's all well and good. But what happens if this potato, so let's say we have a multi-body system. Okay? So you have this potato, wow, with a center of mass there for the potato, and then it's connected via a pin joint to another potato. That's a weird potato. It's like a fish, really, but you know, especially with the eye, kind of see it, right? Say they are connected via a joint. Now that is a pin joint right there. Pin joints rotate without any friction. That's the general assumption, okay? Right? Well, how do we derive the equations of motion for these multiple bodies? Just give me a general, anyone give me a general idea how they go about it? You still use Newtonian mechanics. You can still use free body diagrams, but there's this connecting force here that connects them, right? A tension force, a compression force that ensures that they are connected, okay? So if you have more and more bodies that are connected to that, okay, you have to solve for a whole bunch of tension forces with a system of equations in order to figure out what the accelerations are at any given time, okay, that there's some tension force that ultimately we may not even care about, right? At the end of the day, we just want to know what the acceleration is going to be when we put these forces on the system. The tension force, who cares? Okay? So we would need to solve the equations of motion with multiple bodies and solve using the connecting tension force or contact force. Another way to think of it, right? It can be compression as well. All right? That gets messy real fast. Okay? For something you don't even need. You end up substituting things in one to the other. It gets messy. This gets very messy. With many bodies. Okay? And that's not a crazy thing to encounter in the real world of engineering. We see it all the time. Okay? A robot arm that has, we say, 6 degrees of freedom has 6 bodies. Okay? In 3 dimensions. Okay? It has to get one body, connect to another, connect to another, connect to another. Okay? And so any articulated body, set of rigid bodies, becomes very tricky to derive the equations of motion. But there's a really elegant way that's different than this, that's great for multiple articulated rigid bodies, okay? This we talked about being Newtonian mechanics. Put that little red under there. That's what you probably have seen in college many a time. Who here has ever done any Lagrangian mechanics? Anybody? Oh, prepare to have your world shaken, my friends. So we know from the Newtonian mechanics, you have to sum what? What do you have to sum up to know the accelerations? In Newtonian mechanics, which you learned in free body diagrams. Sum up all the forces. You're going to make me rhyme on a morning? Forces. You got to sum up all the forces. Okay? But as we learned here, there are these forces, there are these internal forces that connect things in these articulated rigid bodies, okay, that we don't even care about. What if we don't even need them at all? Okay? So Newtonian mechanics you sum the forces. In Lagrangian mechanics, you sum energies. Fundamentally different. It'll get you the same answer. You know, the world doesn't operate differently because you approach the equations in different ways. They should give you the same answer. But this one will give it to you far more easily in a very compact set of equations in a very simple form that we can understand. Okay? But the key is that we have to sum energies. Okay? And then once you have summed you summed your forces, in this case, you would use Newton's second law. F equals sum of your forces, your force vector equals the mass times the acceleration vector for all your masses, right? That is true. You know, we didn't disprove Newton. We're coming up with a different way to come up with the same equations more easily, okay? And here, once you sum your energies, you use something called the Euler, he's back, great-granddaddy's back, in yet another context. What has granddaddy Euler not done? Even he's involved with this as well. Euler-Lagrange equations. Okay? All right. They're a little more complicated to write down, but the form that comes out is really nice, okay, once you write it out. And the beautiful thing is it makes it, it also is very easy to put this to sum up all your energies for your system. We'll show you how to go into MATLAB, use the symbolic toolbox to come up with terms for all your energies, shove them into the Euler-Lagrange equation, and it gives you your equations of motion automatically. Okay? We'll do some examples of that in class. Thursday, we'll do some more trajectory optimization first, but we will get to the Lagrangian mechanics. It's super cool. It's super fun. Okay? To me, as much as I love controlling things, there's also a beauty to, you know, setting up your own equations of motion, animating this thing kind of swinging through space, right? So, say Lagrangian mechanics. Reasons about the energies of a system to determine the equations of motion for rigid body systems. And it is particularly useful for multi-body systems. Okay? Now, Lagrangian mechanics is not the only alternative approach. Okay, people talk about Hamiltonian mechanics. There's all kinds of different approaches you can take. Some are based on momentum. Lagrangian mechanics is your first foray into what I call advanced dynamics. Okay? I am teaching a class. Currently, it's on the schedule. I'm teaching advanced dynamics in the fall. One of the things that we cover is Lagrangian mechanics. Okay? I'm also hoping to incorporate some even more modern techniques, such as a spatial vector algebra, which is, anyway, it's wild. But anyway, that, stay on target, Christian, stay on target. Okay, Lagrangian mechanics. Okay, my point is there's going to be a class in the fall that involves Lagrangian mechanics. But this is the survival guide. This will get you what you need to know to simulate some system that you want. Okay? Okay, right? So that's what Lagrangian mechanics does. It's an energy-based approach as opposed to forces. Does that make sense? You're probably wondering what this mysterious equation is, right? Okay, so we need to introduce a couple concepts first, okay? All right. So here's a procedure. For deriving dynamics using Lagrangian mechanics. This is sort of this is sort of the shortcut. This is the procedure, and I'll explain as we go along. I'll put a little caveat. Currently, with no physical constraints, in a future lecture, if we have time, we'll talk about holonomic constraints. But the point is if you can, so you can add constraints, but let's deal without it for now. Okay, just to start with. Okay. Step one, and I'll tell you, let's do this for an example of our pendulum. Okay, just because it's really simple. Here's a mass. Here's an angle, theta over t, and g. Okay? They're a pendulum. Okay? First thing we're going to do is define what we call our generalized coordinates. Okay? Define our generalized coordinates. And call them q of t. And they'll go in a vector of q1 of t all the way up through some qn of t. And what these are, they are degrees of freedom for your mechanical system. It's different than states. They are degrees of freedom. So for instance, in this pendulum, there's only one degree of freedom. There's only the angle it can be at. Okay? So it's going to have one generalized coordinate. In this case, it is theta. Okay. If you had another pendulum on the end of this with another angle theta, how many generalized coordinates would you have now? 2. Thank you. I appreciate it. I know it. Okay. I should be more kind to you all right after spring break. Right? Tell you what. Can we all do, for those who feel willing, let's take like 10 seconds to stand up and stretch, everybody. Okay. All right. If you're willing and able, okay. So just right now, stand up and stretch. This is a free time to do that, or sit and stretch, whatever you want to do, whatever you're comfortable doing. Okay, we're going to get some blood flowing. Oh, for this Lagrangian mechanics. I'm telling you, it's pretty cool. I'm telling you, it's pretty cool. All right. Okay, that's really aggressive stretching. Just, be mindful of your neighbors, okay? All right. All right. So they're generalized coordinates, right? Let's give some examples. Imagine, okay, markers are they've gone from something I write with to something I just throw. Oh, okay. Something I throw. Right? If I had a marker that was just in free space doing all kinds of stuff, right? It would have 1 degree of freedom up and down, left, right, forward, backward, at all 3 degrees of rotation. 6. There's 6 generalized coordinates. Whatever. Okay. We have our generalized coordinates. That's the first step. Okay? Then number 2. Step 2. And obviously, they are things that can vary over time. By nature, there are things can move. They are degrees of freedom. Okay? So in this case, for this example, for our example, q of t is just equal to a vector with just theta of t in it, right? For the pendulum. Simple enough so far, right? Now, we get to the energies part. We're going to sum our kinetic T and potential V energies. Okay. So you sum all of your kinetic energies together into T. So T is going to be equal to, T1 plus T2 up through Tn. Let's just say M when you have M bodies, right? For every body in your system, running out of markers to throw. Yeah, right? This is a body. It's in the air. You can write the kinetic energies for that one body. 1/2 mv squared, 1/2 I omega squared. You remember kinetic energies from physics, right? Okay? And your potential energies, mgh. Remember this, okay? Good. So simple, right? So you have V equal to V1 plus V2 up through Vm for all your m bodies, right? Okay? Step 3, Gesundheit. We compute our Lagrangian. L, where L, by definition, so people often put 3 equal signs, equal to T minus V. Kinetic minus potential. That's what L is. Since we're Lagrangians. It's Lagrangian mechanics after all. Might as well call it that, right? Okay. Then 4. We substitute L into our Euler-Lagrange equation. Okay? All right. Here's the Euler-Lagrange equation. Everyone ready? Okay. It's d dt partial L partial q dot of t minus partial L partial q of t is equal to all of your non-conservative forces. We're going to call it Q and C. Okay. We've defined our generalized coordinate vector Q. We've defined our Lagrangian. We, my friends, know how to take derivatives. And we'll give an example. And on the right-hand side is a vector, Q non-conservative, vector of non-conservative forces for each degree of freedom, DOF. So if this is a passive system, a conservative system, which there's no non-conservative work, it's the vector of zeros. You're done. And those are your equations of motion. What does this ultimately look like? This will, because we're taking the derivative of L, a scalar quantity, it's an energy and an energy. Is energy a vector or a scalar, friends? It's a scalar. Yes. Scalar. But you take the derivative of it with respect to a vector, right? So this derivative is going to be a vector. And you're going to have, in this equation, one element, two element, three element, however many degrees of freedom you have, you're going to have an element in that vector. Okay? Right now, our pendulum only has 1 degree of freedom, so it's going to be just a one element vector or a scalar, right? But it'll be the same thing here. Partial L, a scalar, with respect to a Q, a vector, right? So you're going to get a vector of equations are equal to all of your non-conservative forces, all in a vector. Okay? And that's it. That's the process. Now you might say, okay, well that gives you those give you your equations of motion. Well, let's run this example with the pendulum, okay? With the pendulum, we have our Q of t is equal to our 1 degree of freedom, which is theta, okay? We want to get our kinetic energy, T, and what are all of our kinetic energies in this pendulum? Well, you have, and there's a length L. I forgot the length L. Oh, look at me. I too am bad over spring break, right? It's 1/2 mv squared, or 1/2 I alpha squared, or so it was I omega squared. Okay, 1/2 mv squared. There's an m. What's its v? It's going to be the angular rate theta dot times your length. Okay, let me just write this out real quick. It's going to be 1/2 mv squared. Okay, that's the speed. And our speed v is going to be equal to L, the linear speed is equal to L times theta dot of t, right? We agree with me on that? Good, I see some nods. Awesome, that means my kinetic energy, T, is equal to 1/2 m L squared theta dot squared of t. You agree with me there? I see a slightly slack jaws. I assume that's morning. Okay. All right. There we go. Kinetic energy. What about potential energy? Okay. We're gonna have, that's your mgh, right? Well, the height of this thing. Let me just scroll up here. So that's v. It's going to be mgh. What is h? Your height. Mass, gravity, height. Well, your height relative to the bottom. You can choose any relative point. It's not going to matter. It's all going to come out in the wash. But it's going to be what? minus L cosine of theta, because we want the, remember your trig, we want that. So we want, we want cosine, so we want the adjacent over the hypotenuse or whatever, right? So it's going to be equal to minus L cosine theta of t. Okay. So therefore, potential energy V is equal to mg quantity L cosine theta of t, or just to simplify it a little bit, equal to minus mg L cosine theta of t. Right? Now our Lagrangian. What's our Lagrangian? By definition is equal to t minus v. Write that out. So it's L is equal to t, which is that right up there, 1/2 L, 1/2 m L squared theta dot of t squared minus v, so minus negative mgl cosine theta of t, right? Simplify that by getting those negatives, the double negatives. We don't like those. We don't like those double negatives. Okay? Got exactly half of a smile out of that one. It's good. I'll take it. All right. 1/2 ml squared is theta dot squared t plus mgl cosine of theta of t. Stop me if I missed anyone on anything, because what makes Lagrangian mechanics suspiciously simple. Okay? Now we have the Euler-Lagrange equation. And some of this might need a little bit of refreshers or introduction for you on how you have all these different partial derivatives versus ordinary derivatives. Okay? It has d dt partial L partial q dot, I'm going to skip the of t, right? Minus partial L partial q is equal to your q non-conservative, right? So let's look at the individual terms here that we want to compute. We're going to want to compute this partial L partial q, okay? Partial L partial q. Well, this is our L right here, right? And our q, what's q, friends, for our problem? Theta of t, exactly. So in partial derivatives, if something is not that term, treat it as 0, okay? So here you see a theta of t there, right? So that term is going to be relevant to the partial derivative, because the theta of t is right there, right? But what isn't is theta dot of t. You can treat that as zeros. You can treat that as a constant, so it will become 0, okay? So the only term we're going to want to take for our partial q over here is that. Does that make sense? So it treats, even though you see a theta there, it's theta dot. So it's not relevant to that partial derivative, okay, right? Just a little, that's the quick hack, I should say, okay? So we only have to worry about this term. So we have the partial of this with respect to theta, right? So the derivative of a cosine is negative sine, so it's just minus mgl sine of theta of t. Okay. So that's this term right here, right? Whoop, that. Now let's move on to this and break it down with partial L partial q dot. Okay? Gesundheit. So let's look at partial L partial q dot. Similar rule. We go back up to our Lagrangian and we say, friends, this is theta, not q dot. So keep in mind that, q, as you know, is equal to theta. And q dot is going to be what, friends? What's q dot going to be? Theta dot. Thank you. Right? So there's no theta dot there. That gets treated as a constant and will go away when we take the derivative, leaving this term, right? Okay? So partial L partial q dot is going to be partial L partial theta dot, and that's right there. So you're going to theta dot squared, so it's going to be 2 times 1/2. It's going to be 2 times 1/2 L squared theta dot of t, right? And that's just going to become L squared theta dot of t. Oh, and I forgot an m. Did I forget an m? I forgot an m. I forgot an m. No. Forgive me. I forgot an m. ml squared theta dot of t. Okay? So we've done this term, right? Let me use some happy little colors just so we can correlate these things. Think, oh, look at that, that's blue. Oh, look at that, that's green, assuming you can see these colors. I apologize if you can't, okay? Same idea. I'll draw arrows so it's clear, right? We have almost all our terms, but we, in fact, now need to take our time derivative of this thing right here, right? So this is an ordinary time derivative. Excuse me. We want to do d dt of partial L partial q dot. Forgive me for leaving out the of t. It's going to be d dt of ml squared theta dot of t. Right? This is not too hard, right? We have theta dot of t. What's the time derivative of theta dot of t? Theta double dot of t. This is ml squared theta double dot of t. How about that? How about that? Okay, well, now we have both terms, right? I'm going to make this red. 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 They call me red. Okay? I'm quoting Dr. Seuss books. You can tell I'm a new dad. Okay? All right. So we have those terms. In our Q non-conservative, we have no non-conservative forces. So we're going to say there's no external forces pushing the pendulum. There's no friction, which would be a non-conservative force. I didn't include any of that, but if you did, you would put it in that term right there. Okay? So I'm going to say Q non-conservative for our only degree of freedom is 0. If you wanted to apply an external torque to that angle, you would put a little tau there. Oh, that's the applied torque, which we don't have currently. Okay? So now we have the Euler-Lagrange equation. So this red term here, that's going to be ml squared theta dot double dot of t minus, minus this term here, which is minus mgl sine theta. Right? Is equal to Q non-conservative, which is 0. Okay? So those are our equations. But if we want to actually simulate our system, we're going to need to know what our accelerations are and solve for that, right? That's what we did in the past for our pendulums. So let's solve for our accelerations. Okay, so let's put all this on the other side. Negative, negative, bad, bad. So it must become a positive. But they're going to put it on the other side. It's going to become negative again. So it's going to be ml squared theta double dot of t is equal to minus mgl sine of theta of t. These two negatives become a positive. Put it on the other side, become a negative again, right? Let's start canceling. Boop, boop, m's gone. Divide both sides by L squared. This becomes theta double dot of t is equal to minus g over L sine theta of t. Does that look familiar, my friends? It should. We've said it way too many times this class. Different approach. Same answer. Funny how that works. Questions so far? Right now, yes, question. I mean, they are forces that add or remove energy from a system, from the system. So a friction, classic non-conservative force. And I mean it in the sense of your physics 1 class, okay? If there's a motor, right, that is adding energy to the system or can remove energy from the system, that's a non-conservative force. All the other, the potential and kinetic energies, they will exchange forces. They'll exchange energies, right? You know, just to abuse these poor markers, when it's in the air, assuming no air resistance, right? It's all an exchange of potential and kinetic energy. Okay? And the ways that the Euler-Lagrange equations work is that you have all of these equations in a vector, and it is figured out, when you set it up this way, it shows how the energy is exchanged between potential and kinetic energy across these different degrees of freedom. So if you had, for instance, 16 spring masses all connected to each other, you could set that up with Lagrangian mechanics. You could do that with Newtonian mechanics as well. Probably did it in controls 1 if you took controls 1, or system dynamics. Okay? That's what I mean by non-conservative forces. If it's a motor, non-conservative force. Friction, non-conservative force. Spring, conservative or non-conservative, friends? Conservative, right? And that would be, so where would the spring show up in our Lagrangian mechanics if it's a conservative force? Potential energy, right? Anyone remember 1/2 kx squared? The amount of potential energy in a spring? It's potential energy, friends, added in there. And the math will work. Okay? Other questions? None. Perfectly cromulent. Awesome. You all get it. Let's do. But I said this is something that this was right here. This is a more complicated way to get a single pendulum, right? Where things get more complex is where we have multiple bodies connected. Okay? So let's go, my friends, to the pendulum on a cart. Okay? Do another example. Multibody. Multibody dynamics. So pendulum on a cart. Okay? So we're going to have just a mass with a cart. Sorry, we'll call it M1. Oh, goodness. M1. We're going to have M2 on the end here. We have some L. We're going to have some position x of t. Yeah, x of t. Live dangerously. Okay. And the angle is going to be defined from the vertical as being some theta of t again. And we're going to be under gravity again, friends. We're not going to be in deep space. Or in the vomit comet, wherever there's not gravity in your reference frame or whatever. So anyway, let's use Lagrangian mechanics to get the equations of motion of that. Okay? How many degrees of freedom do we have for this system? 2. Cart moves left and right. The pendulum swings around. Okay. So our generalized coordinates Q of t are x of t and theta of t. That's it. Okay. Now, let's sum our energies. Let's do our potential energies first. Potential energies are easier for each of our bodies, okay? So we have two bodies, M1 and M2, right? Okay. If you have a spring in between, keep in mind you need the potential energy of that spring in there. There's no spring today. You just got to sum up all of the potential energies that are in the system, okay? For gravitational potential energies, you definitely need it for each of the masses, right? For M1, that potential energy is always 0. If we just arbitrarily decide height h is equal to 0 at the ground, it's always 0. V1, 0. Anyone confused by that? Okay. Plus potential energy 2. Okay. Well, that's going to be mgh for mass 2 times g. And what's our h? Well, it's the same thing that if it's down at angle 0, it's going to be, so it's minus L if it's down at angle 0. It's going to be L at the top at theta equals pi. So it's going to, if you work out the trig, it's going to be minus L cosine theta. It's the exact same thing as our last pendulum, right? A minus L cosine of theta of t. Potential energy. Done. Kinetic energy. All right. I'll tell you, this is where it's helpful sometimes to establish a vector from some 0 point in Cartesian space. Because it might become tricky in a moment. You'll see it's slightly tricky. Okay. Not too bad yet. But if you're ever confused as to what the speeds are of an object or the position of an object, just define some 0 point, 0, 0. Then say, hey, here is what the vector to our first body is, depending upon what our degrees of freedom are, right? So if we were to draw some vector, let's call it, make it red. Some vector from some 0 point to our mass, I'm going to call that R1 vector. I'm going to call this vector to the second mass, I'm going to call that, creatively enough, R2. So if I want to know the height of those objects, I could compute the vertical component of those vectors. And those would give me the heights for my mgh's, right? 0 and minus L cosine theta. Question? Mm-hmm. So you're talking about doing relative velocities as opposed to absolute velocities of 0. You can do it that way as long as you're remembering to add up all the relative velocities together to give you a total velocity vector in the world frame, as we would call it, like in the inertial reference frame. Okay, just to bring back some classic physics into this. Okay, but it's a handy trick just to write these vectors out, because then if you're ever confused as to what the speed of these masses are, all you got to do is say, well, what's R2? Take the time derivative. That's the speed. That's the velocity, I should say, right? If you're ever confused, because that's something that you're actually bringing up a great point, which is when you're coming up with the velocity of this mass, you can't forget what? Velocity of this mass, right? They're attached. Okay? So T is equal to T1 plus T2. Okay? T1 is easy. That's 1/2 mv squared for our mass 1. And it's also 1/2 mv squared for this mass as well. Okay? The only tricky thing is that m1 is 1/2 m1 x dot of t squared, right? That's your velocity. It's constrained to one dimension. Okay? plus C2, right? And this is where it's very, very handy to have a more formal definition of kinetic energy. Okay, we say speed squared, and that's true, right? Another way to write that in a way that is very correct with vectors and vector math is you would say it's, hey, it's 1/2 times your mass, in this case m2, of your velocity vector dotted with your velocity vector dot product. That works in 1, 2, or 3 dimensions. If you had a 4th dimensional Lagrangian mechanical system, it would work for that too. Okay? Right? This is the more formal way, so we just sort of note. Kinetic energy translationally, meaning in translational directions, rotation's different. Right? Translationally can be formally written as P is equal to 1/2 mass velocity vector dotted with the velocity vector. And you'll recall the dot product is first element times first element plus second element times second element plus third element times third element. You have more, you have more. Okay? So what's helpful is if we write what is V2. And we'll start by saying, hey, what is R2? What is that vector? Okay? What is the position? I'll go back to it in just. What is that vector right there? Okay? Well, it's going to be this vector plus this vector, right? So for the x component comma y component, right, it's going to be x of t for the x component plus, I'll scoot back up, plus whatever that component is there, going to be L sine theta. You have to trust me on the trig, or maybe you're trigonomagicians. Hopefully you would agree with me. All right, plus L sine of theta of t. Right? And then for the vertical direction, the vertical component of that first vector is 0. It ain't going up. That cart's on the ground. We're pinning that cart to the ground. There's no friction as well. I probably skipped over that part. And the vertical component is minus L cosine of theta of t. Right? So if you're ever confused as to what the height of that object is for MGH purposes, there it is, right? What's the velocity vector? Well, I'm glad you asked, my friends. Okay? It is the velocity 2 is equal to R2 dot, right? Time derivative. So it's going to be the derivative of that plus the derivative of that for the x direction. X dot of t plus L cosine of theta of t. But don't forget the chain rule, friends. It's an ordinary derivative, so it's going to be theta dot of t cosine of theta of t. That's the chain rule. You have to pull out. That's the rule. Derivative of the inside. Okay. Now, my friends, move on to the vertical component. There's going to be L cosine theta of t. That's going to be, it's going to be positive sign, so it's going to be, sorry, negative sign. It's going to be L theta dot of t sine of theta of t. This switches to a sign, throws a negative sign out front, gets out the double negative, so positive, positive. Chain rule gives us theta dot of t, sine of theta of t. Okay? That's R2 dot. So our velocity. So if we take the v dot v, okay, that means that that v dot v is going to equal that times itself plus this times itself. Okay? So the term's going to get tricky pretty quickly. Okay? And we haven't even taken any partial derivatives yet. Oh, fun. But that's okay. Do we have something called the symbolic toolbox in MATLAB to help us out? We do. Okay. You can do it by hand. Let's do it. Okay. All right. So T is going to be equal to 1/2 m quantity, the quantity, x dot of t plus L theta dot of t cosine of theta of t squared plus quantity L theta dot of t sine of theta of t squared. Okay, that's t. Now we can FOIL these out, first, outer, inner, last for these squared terms, or at least particularly for this squared term. Let's do that for the sake of completeness. So that's going to be t equal to 1/2 m. First times first, that's going to be x dot squared of t, x dot of t squared, I should say, plus 2L x dot theta of t cosine, theta dot of t, cosine of theta of t, plus L squared theta dot squared theta of t cosine theta of t. And then I need to add at the end. Oh, this is m. I've also, by the way, isn't this m1? No, this is m2, right? m2, and this is all t2, right? Okay. I'll stop there for a second. Okay. You notice the dynamics are starting to get pretty complicated, right? You don't see nothing yet. Okay. So let's move forward. Where are we on time? Low on time, but I want to show. So let's see if we can get through this. So we have t is equal to t1, t2. That means that t, again, is equal to t1 plus t2, which is going to be equal to the first term, which is 1/2 m1 x dot of t x squared plus 1/2 m2 x dot of t squared plus, I'm distributing here, right? This to there. Now I'm distributing 1/2 m2 to there. There's a 1/2 and a 2, so it's going to be m2 L x dot of t. I'm going to move this down to the next line. I'm running out of space here. m2 x dot of t theta dot of t cosine of theta of t plus 1/2 m2 L squared theta dot squared of t cosine of theta of t. So that's all of t. Okay? That's just me applying trigonometry, a little bit of vector multiplication, gets me that answer, right? The point is I had to sum up my kinetic energies and potential energies, right? Okay? Now we have our Lagrangian. L equal to t minus v. And we're going to need to know a few things. We're going to need to, because we need to know if the Euler-Lagrange equation, we need d dt, partial L, partial q dot. I'm going to get rid of the of t's for my own carpal tunnel purposes. Partial L, partial q. I have no non-conservative forces. I'm not putting any friction on this thing yet. I'm just going to say that's 0. Not putting an external force on it yet. This, by the way, is how I computed the equations for your pendulum on a cart for your first homework, by the way. Okay. So let's start with some of these terms. Partial L, partial Q. Okay. Well, I guess we have to write out L. Oh my goodness. Do we have to? I guess we kind of have to. It's not too bad because thank goodness the V is really simple, right? Minus M2 GL cosine theta. L is equal to minus M2 GL cosine theta. Oh, that's V. Oh my goodness. That comes second. Professor's losing his mind. Okay. That whole T minus V, so it's T, all that stuff, minus V, which is thankfully simple. That's 1/2 M1 x dot of T squared plus 1/2 M2 x dot. Oh, I forgot the, okay, we're getting rid of the of T's. You won't tell anybody, right? Right? Squared. Plus M2 L x dot theta dot cosine of theta plus, did I miss a term? No, I did not miss a term. Okay. Did I not include a term somewhere? No, I did. I did. Plus 1/2 M2 L squared theta dot squared cosine of theta. Okay, that's my Lagrangian. So partial L, partial Q. I'm looking for my Q's, keeping in mind that I have 2 Q's now, right? So now that means it's partial L, partial my first Q. What is my first Q, friends? X of T, which I will, X okay? Yes, question. Did I screw up a sine term? I forgot the sine term. Okay. Got the sine term, thank you. It's right here. So T minus V, so we just got to add here. We just didn't add it. It needs to be added in. And so it's, what is it? L squared theta dot squared cosine squared of theta. And I have to subtract out the potential energy as well. Getting, which is M2, so it's minus be plus MGL cosine of theta. So we have right way up high, that's the V. Okay, thank you. So I added this term, and I added this term. Okay, and my zeal. Other questions? Any other catches? All right. Don't drink and do Lagrangian mechanics, friends. Okay. I'm not drinking, to be clear. This is sober math, unbelievably. Okay. All right. So back to our partial L, partial Q. What are our Q's? X and theta, right? So we're going to have 2 elements of this vector. It's going to be partial L, partial X, partial L, partial theta, right? So it might be helpful to write these out. So it's partial L, partial X. Anyone see any X's? I see none. I see X dots. Whoop. Partial L, partial theta. Do I see thetas? Yes, several. I see several thetas. I see cosine theta there, cosine theta there, cosine squared theta there, cosine theta there. Was that supposed to be a sine squared? Oh. Okay, I'm on my own. That's a sine. All right, put it in red. Sine squared theta. How embarrassing. Is that right? I'm just going over. I'm just doing a quick check here. I didn't screw something up. Because right here we also need the plus L squared theta dot squared sine squared theta. Gosh, you can see why we start using MATLAB symbolic toolbox very quickly, right? Okay. All right. So partial L, partial theta. So you're going to have a whole bunch of terms here. Thank goodness it's a partial derivative, so you don't have to worry about that. Okay. Oh my God, we're not going to have time to finish this today. Okay. But let's try to get through at least some of it, okay? So we can follow at least the formula. Okay. Because you're going to get all these equations, and at the end you're going to be like, my goodness, what do I do? How do I even solve these equations? They look complicated enough. Well, there's a cool trick you can do. Okay. There is, so let's see, partial L, partial theta. There's theta there, theta there, theta there, theta there. There's going to be minus m2 L x dot theta dot sine theta. And then for this term, it's going to be so it's going to be minus 1/2 m2 L squared theta dot squared sine theta. That's this term. Thankfully, we get to treat that as a constant. That's nice. And we've got plus 2 L squared theta dot squared sine theta cosine theta. That's the 2 is a sine squared, so it's going to have the chain rule outcomes, the derivative of the inside, which is cosine of theta, minus m2gl sine of theta. So it's these 4 terms, right? Okay. And you have to do the same thing now, partial L, partial Q dot. And then once you're done with that, you have to say d dt of partial L, partial Q dot. Could equal a lot of things. I leave that as an exercise for the curious, right? Go through that. And we could write this all out. This would take a huge page, right? Well, what you're going to have is a whole mess of equations that are basically going to say, hey, it's going to look like this. It's going to say partial L, partial side. This is d dt, partial L, partial x dot, minus partial L, partial x, and d dt, partial L, partial theta dot, minus partial L, partial theta. They're all going to equal 0 and 0. And what's going to happen is that inside of each of these equations, on this side, there's going to be some combination of x double dot and theta double dot that you will need to solve for these. That's what we did with the pendulum. We just solved for, say, the theta double dot, but that was easy, right? It was really easy to solve for theta double dot up above for the single pendulum, right? However, we're going to have probably x double dots and theta double dots in here, x double dots and theta double dots in here. 2 equations, 2 unknowns. So we can use a little bit of matrix math to help us solve it. Okay? So there is a common form to write the equations of motion for multi-body systems, called the manipulator form. Typically, they think people are thinking of like multi-body, like robotic manipulating arms. That's kind of where it comes from. At least it's relevant. That's the way I think of it, I should say. Where you have a vector, q double dot. Those are accelerations, right? These things that we often want, right? Okay? And you can write it as the vector q double dot times a matrix m of q. Okay? That if you work out this math, if you did your math for Lagrangian mechanics correctly, every single term that has a double dot, x double dot, theta double dot, will at most be multiplied by something that has a q in it. Not a q dot, not of speed, but a position. Okay? Plus some c q of q dot plus g of q equal to q non-conservative forces. You might notice that I left out some of t's here for all the q's. That's of t, that's of t, of t, of t. Okay? Called manipulator form. Why is this handy? If you can put it in this form, which we can and will in this class, all you have to do is take all of these terms, move them to the other side. Okay. These will be vectors. The matrix. Okay. What you can do is then say, hey, well, m of q double dot of t is equal to minus c of q dot minus g of q plus q non-conservative. Put all this together. How would we solve for our good friend the accelerations? How would we do that? This is a matrix. Anyone taking any linear algebra in their lives? You multiply both sides by the inverse of that matrix on the left side. Q double dot equal to m inverse of q minus c of q dot minus g of q plus q non-conservative. Okay? And you can get these matrices, they have special names. M of q called the inertial matrix. It's like masses. Okay, and it's got a very particular structure. If you've got masses, it's just masses down the diagonal of a matrix. That's all it is. Very simple. Okay, if there's rotational inertias, it's a little more complicated, but not much more complicated. Okay, M of q called the inertial matrix. C of q is called the Coriolis term. Who's heard of Coriolis before? Yes, what is it? That's okay, but you remember it, all right? It's things that are dependent upon speed. People talk about if you shoot a cannon on the Earth far enough, you will notice that it veers off course due to the rotational speed of the Earth. We call that the Coriolis effect. There's a myth that Australian toilets go flush in reverse because of the Coriolis effect. That's not true. Not true at all. I shouldn't even mention it, right? But it's, or like if you are on like one of those playground go-around things where you're like on a thing and you're spinning, and then from your perspective, like you drop a ball off of it and it seems to veer off in a weird direction. That's a Coriolis effect. It's speed dependent, right? And it's speed dependent because, like I forgot here, it's C of Q, Q dot. Dependent on both positions Q and speeds Q dot, right? And G of Q, that's your gravitational term. Right? These are all vectors. That's a vector. M of Q is an inertial matrix, which you can compute using the Jacobian, by the way. That's what we'll do when we're actually coding this up next week, I believe, for our class. I believe we'll do it next week for our coding lecture. Fun quick story before you go. When I was on Survivor the first time, 7 years ago, before we were left on the island, the press came out and they want to take video of us. And they're like, you're a science guy, write an equation in the sand. Here's a stick. Okay? So I wrote this. Okay? And they said, that's great, but our Instagram shorts are only a minute long. Can you make a shorter equation? So I'm like, sure. F equals ma. There you go. Shorten it to Newtonian mechanics. All right, that's it. We're at the end of class. Thank you all so much. Have a good day.